Okay, to be in this session, using some material I pulled together in response to some student questions in this class, but also in response to some of the patterns we saw within ID1. And this material draws on some ideas I think all of you should have encountered at some level before, but may not have approached in the way I'm going to be approaching it here. And with the emphases that I'm going to place on the use of specifications within your projects. So in many ways, this should be review, but maybe it will unify some understanding on a couple topics that are often approached sort of separately and in isolation from one another. Okay. So one of the recurrent themes that I've talked about in the reviews of your IDs, you're in class, is the centrality of effective testing for building quality projects. And in turn, the need to promote, particularly on the part of developers, testability for your system. And in fact, in our next session, Thursday, we're going to be really hitting on this further in ways that directly relate to your projects. But I wanted to address one particular component of it, of the ways in which we could build testability, but something with much broader impact than merely its role in testability, as important as that is. Impact in allowing us to divide up work within a system, to more effectively understand systems, more effectively review systems in whether it's in pull requests or in inspections or other areas. Allows us to start work in one area of the system while another is not yet started, another that it uses. And I want to ground this just briefly in the fact that achieving success within the software sphere now, being able to thrive as a software company, a technology company, involves grappling with the complexity of modern software. And I submitted to you that one of the big motivations for doing effective risk management is to allow you to scale to achieve the construction within a timely, within budget fashion of more and more complex software. So software is structurally, and while it runs dynamically, very complex. And there's lots of interconnections. And this is really important for understanding some of the principles we're going to be talking about today. One part of the system will depend on other parts of the system. I don't think I have to expand on that too much, but we'll see some examples. But one part may call another part or use classes from another part, right? Use a layer beneath it or two beneath it. And the whole is greater than the sum of the parts for the system. They have to play together nicely. The relationship, it's not just the pieces of the system, it's the relationships that are key. And this complexity is a major challenge to deal with in software development. It's a major barrier for effective delivery of quality code. And a failure to handle that complexity comes out in projects that are over budget, beyond their expected time, that disappoint stakeholders, and fail to reach their potential. So one of the key ways in which we deal with complexity is modularity. Can anyone say here, when I say modularity, what do I mean? Here, just very roughly, yeah, Tim.
That small block put together.
Yeah. Divided up into pieces, where those pieces have to play together nicely with other pieces. They're not solids, but those pieces can be reasoned about, built, tested, reviewed, modified, evolved separately from others, right? And through effective modularity, we seek to sort of decouple these pieces of a system, allow us to work on one piece separately from working on others. And there's a separation of concerns that often happen. Different pieces deal with different problems, different challenges, different types of work that have to be accomplished. Some involving the data layer, some involving maybe the business logic, some involving UI actions for showing a time graph, others UI actions involving, the 3D display and the Oculus of the embedded data, for example, right? Maybe some parts deal with vaccination schedules, and other parts deal with keeping track of a family's history or the history of a given person with respect to past vaccines, right? We have a separation of concerns, and different types of concerns are separated out, right? And a key element, as we'll see, is this idea of kind of using one piece of the system, one module, can know about other modules, make use of them without knowing about the details of the other pieces, right?
I thought you were going to go full whiplash.
So we can have one piece that makes piece A that makes use of pieces B, C, and D without a need to know everything about pieces B, C, and D. So I can call off to B, call off to C, call off to D, without it having to know about all the details. Why not allow it to know about all the details? What's that?
Details to you. Well, things that obviously you're doing that.
Yeah. We don't want every time B evolves, have to change that. We don't want every time C evolves for the creator of A to have to redo their code or go over their code to see if it needs to. We want to build things in modular ways and couple them together without the madness of each part affecting all the other parts, and a change in A and a change in B having to lead to a change in A. We want to be able to modify these components separately. Now, modularity done well can allow this sort of divide and conquer, but to achieve these elements, to achieve the ability to reuse these pieces, we need to grapple with this challenge of being able to modify things easily without and separately. And it turns out we know how to do that well, but it requires a certain amount of discipline in the form of good specification. So done well, this has many benefits. Code creation. I can create A before B, C, and D are created. I can modify C without having to modify A. I can test A without having to test all of B, C, and D of necessity. Although often I want to test them sometimes in an integration test together. I can test C without testing A by calling it in a different mechanism. And mocking is a mechanism that helps me. I can debug them separately and reason about the behavior of C and see if it's violating some properties, some assumptions that it should guarantee. I can review B, C, and D separately from A, and I can have people who specialize in different layers. I can have someone who specializes in the data layer, someone who specializes in the UI and dealing with the output of the time graph or what have you. So the key to achieving effective modularity is abstraction. And you may have heard this term bandied about in many different ways, having to do with sort of high level understanding and generality. But I want to define it in a certain way, because I'm going to be taking a certain stance that's going to unify things that are often dealt with separately. Abstraction, I'd like you to view as the process of putting aside certain detail to treat many particular cases, many particular circumstances as the same. Now, we're going to see this includes many pieces, many different ways of understanding abstraction. So in abstraction, we recognize that there's commonality that we can draw. We can abstract out of many different cases, and we can treat them all as kind of variants of just details that are variants of a certain pattern. And by putting aside those details, by allowing us to handle a variety of particular cases equally, abstraction allows flexibility. The same abstraction captures many particular circumstances. And we can go between those circumstances without having to modify the abstraction. And we'll see that comes in two different ways. One is abstraction by parameterization, where we can pass the same abstraction, maybe that adds two vectors, many different places in the code base. We'll call the different pairs of vectors. We'll add them together. Rather than hard coding vector addition and all these different places, we just call one thing. So we're putting aside the details of exactly on what vectors it has to add them by parameterizing, by passing it those. Another case is, as we're going to see, that we alter the implementation of the code. We can swap in different implementations without worrying that it's going to break all the different things that use this abstraction. And the idea here is one abstraction allows us to handle many cases by hiding the details and allowing many cases to be treated in basically the same or very similar way. So I'm going to be talking here about two types of abstraction, both of which are really important for your project. Both of which I'm seeing under featured, under invested in within ID1. And I want to see them featured more prominently for both of them. Abstraction by parameterization and abstraction by specification. Okay. And I just alluded. And I'm going to go through examples of each of these. You're going to see why both hew to the same basic pattern. Hiding details, handling many particular circumstances in the same basic way, and having flexibility because of it, being able to reuse the same abstraction with no change for many particular circumstances. Okay. But the type of change they're going to handle is different. The first is going to handle many particular types of use in different circumstances in the code. The second is going to handle many particular implementations that all meet the same interface. Okay, so first I'm going to talk about, appropriately enough, the first of these. And then I'm going to go on to the second. So we're going to have example one, example two. Okay. So first is, and forget the trivial nature of the example, but by simplicity, I'm trying to get to the heart of the matter. Okay, so we have some code. Foo, bar, baz, zap, right? Quux, maybe. And each of them includes code to add to vectors. And right now, they're all inline. So we, in this place, we loop through V1, and we're adding V1 and V2. I don't show the details of it. Here we loop through my vec, and we're adding it to his vector or something like that, right? And there may be many other circumstances. So if you see this code, what's one of the key attributes of someone who is aspiring to be a strong software developer is to be able to recognize code smells, be able to recognize when quality is just not there. What's the problem with this code? It's duplicate code. Conceptually, it's duplicate. It's not textually duplicate, right? This says my back, that says V1. But it's basically the same pattern as we say in Latin, mutatis mutandis, with just inessential details change, right? The variables are different, but it's the same basic relationship, the same basic behavioral pattern of adding together vectors. And if you had 10 of these, that's a fair bit of repeated code. Now, what's the problem with this code? Okay, so you recognize the code smell, but why does it have such a foul smell? Like, why does this lead to problems?
If we're adding vectors a different way in different times, or we need to make a fix that will affect all of them, or you only affect one of like Canada in different places. But
Colin has it. That's exactly right. So if we want to modify, like maybe we want to put in an assertion that the two vectors we're adding are the same length. So we don't do something silly, right? Like add a vector with 4 elements to a vector with 3 elements, right? You want to assert that they're the same size. That's a precondition that we have in mind. We might put in an assertion in one place. And that's great, but we really want to follow through every place, we put in that assertion that this is happening. And we might not remember, right? Because there's all these examples that are essentially the same. They differ only in inessential ways, but we might not notice where they are within the code base. We might forget all the places you could apply this, right? Now, this is a nice quality check to help enhance testability, but you can imagine if it were a bug fix, that would be even more problematic. We might fix it in 9 out of 10 cases, but forget the 10, and it leaves the bug in there, right? So one of the problems that this duplication, this code clone has is it's brittle in the sense that if we want to evolve it, it's easy to forget some particular examples of it. And we don't have one place to go. We have to go to many places, despite it being basically the same fix that we're putting into place conceptually. So one way to deal with this that I assume all of you are deeply familiar with is to carve out an abstraction, right? This is just begging for an abstraction. It's like if you see this pattern again and again, whether it's code like this or some sort of complex condition, it's just begging to be reified as an abstraction. It's just yearning to be turned into some reusable piece. That's how I view it as a software engineer. And this is code up with which I will not put to adapt Winston Churchill's act. Okay, maybe that doesn't resonate. This is the type of English up with which I will not put. No, okay. Moving right along. So here we have these different circumstances, and instead of having the same brutal code repeated again and again, which students often give me, and it causes me distress of sometimes an almost existential sort. I mean, it's disturbing to the point of causing me to leap up from my chair. Instead of seeing code riddled with repeats of the same concept, we give it the dignity of a face upon the world. We abstract it out into, we reify it as a function here that we can reuse in many places, right? And then if we have to fix it at one point or improve it, like by adding a quality check, like an assertion, we can do it at one place because conceptually it's one change. We shouldn't have to repeat that one change n times for the n places that are there, only to realize later we should have done it n+1 times, right? We have one place to go for it. I hope your heart starts to yearn for this too. I hope you seeing this would give you a queasy feeling in your stomach. And that at some point you realize that writing code like this not only lacks a sense of dignity, it lacks a sense of shame to write code like this. I mean, it's like an affront, you know, to beauty and truth. So we carve off a function, right? An abstraction. We turn this, we have an abstraction that represents some concept, right? Adding a vector. Yeah, pretty straightforward concept. It's waiting to be born. It's yearning to be born here. And we give it birth, add vec, right? And then we can just reuse it from any place. So we carve off a function. We have this sort of latent thing that is in our code that is just waiting to be named and given the dignity of the recognition of what this is and that it's reified as a piece of the code. Okay. It's given a name, it's given a purpose, it's given preconditions and postconditions. So here, the details being abstraction over are the differences between different contexts of use, right? Like here we're adding vectors v1 and v2. Here we're adding my vec1 and my vec2, right? But this abstraction we've added abstracts over those details, right? Oh yeah, whatever the details of the particular vectors are, whatever their names are, you can pass them up as the arguments to this function, right? So it abstracts over the vagaries of these details, right? The happenstance of what the names are, the vectors you're passing it. As long as there's two double arrays, we can pass them in here, or two double vectors, depending on your language, right? So this hides details. It hides the details of exactly what the names of these are, and allows us to reuse it in many, many places, right? It allows us to use it in many specific circumstances. Are we okay with that? It hides the vagaries of what their names are by allowing you to reuse the same mechanism by passing it different arguments, right? You comfortable with that? Very, very basic stuff, right? Okay, good. And there's many ways in which we perform this in our code. And at this point, you may have first seen this in 141 or 145 or something. It should be so basic to you. It's almost like, being able to take a drink of water or something, right? I hope. That's not the impression I got by looking at your code, but it should be that basic to you. And we see it in many forms. Actually, some of you will recognize that type parameterization is another way in which we abstract over circumstances. We have a linked list that can be applied for a linked list of doubles or a linked list of ints or a linked list of hash tables or a linked list of images or a linked list related to the lecture I gave yesterday for 340 of figures, right? And we can have type parameters that allow us to have, a linked list of fill in the blank, of pairs or what have you, right? Okay, so I would hope that this process is so familiar, it doesn't really need much, mention. But it's worth noting that this helps many aspects of software development, code creation. What is it? Why does carving off these kind of modules, these methods or functions that represent these chunks of work, like adding two vectors, why does that help separate code creation? Anyone say? Why not just leave them in the code? By carving them off, what does it allow us to do? Yes. Randall?
Yeah.
Yeah. So say it again, Randall. Good. So I think that would include what I'm looking for. But basically, the person who's writing this code, foo, can operate separately from the person who's writing this one, right? The person who's writing advec can be writing it at the same time foo is being written. By dividing it up, we can divide and conquer. Right? We can have different people working on different pieces. Familiar? I hope this is all familiar to you, right? We can modify things separately, right? That was a lot of what I was emphasizing before. Instead of having to modify all these different places in brutal succession. Hideous. I tell you, hideous succession. Instead of doing that, one after the other in heinous detail, I can just modify it once. Like I can insert this assertion in one place. Yeah? Do you get that? So it reduces the madness involved, right? In trying to make a single conceptual modification instead of having to be modified n times in the code base. For each variant of it, I modify it in one place. And it's home. A home word. I can test it. Why is carving out advec like that? Why does it help testing? Why do I say that it helps testing? Yes, Connor with an E.
Like test individual functions and make sure there's no word.
That's right. Yeah, so functions here are carved out as natural units of work to be done, right? They're natural chunks of work that have to be accomplished. Those abstractions are reused in many places because they represent something meaningful that has to be accomplished or done. And by turning them into a self-contained piece of code, a module, as it were, a function, a method, even a class, we then have some code that has a very defined job in it, right? So it's a very defined job. And it has a very specific thing that it accomplishes, right? Path given two vectors of equal size, it should return a vector that's the sum of the successive indices of each of the two vectors, right? And that's a very well-defined property that we can check. Does it, in fact, do that properly, right? Are we okay with that? We can test it. And notice how I put the assertion in there to increase the testability of it. So if there's a problem, it's detected early within this. Testing, as it were, a precondition of this, as we'll see. But it helps because we have these well-defined places we can test, right? That have well-defined jobs to do. If I hadn't done that, if I had left them in this code, how would I kind of get after this code here? This here code is in the middle of some long piece of code. How would I test that particular piece? I have to test the whole hairball of code, right? That contains it. Somehow I have to, if I want to test this particular component, I have to kind of figure out, how to look at what it's doing here in the middle of a big tangled mess of code. It's a nightmare. It's much more effective to carve it off into its own piece that I can test separately. Do you accept that? Are you comfortable with this? We're leading up to a different type of abstraction by specification. That's where this is going. But do you accept this basic premise that carving it off helps increase testability? Then please give me code where things are carved off. I beg of you. I entreat you. I exhort you. Okay. Okay. Yeah. No. I inveigh upon you. I hope I can encourage you to do that. So it can help with testability, right? Can help with testability. Can help with mocking. I could mock out. Now, it turns out to be much slicker with the type of abstraction we're coming to, but I could create a fake version of AdVec whose job in life is to test the vectors passed into it. Are they of the same length? And it returns a vector of that same length with random things in it or whatever. It's sort of a crude approximation to it that I can put in place before the actual thing is created. I can debug it more easily because I can note during debugging what the job of this code is supposed to be and see if it accomplishes that. I can review it more easily. I could give it out to my groups to review. I could put in a pull request, this particular function, and you could have a sense of what its job is in life, what it should do, and you could inspect it rather than seeing it in the middle of some big, hairy bunch of code. And different people may work on different functions. Okay, so that should be largely review. I hope those ideas go back to, if not 141 to 145. Perhaps you would have seen them in 214. I hope they were featured as well in 270 and 280, maybe even. But I want to make sure that those principles are clear to you, right? Now I want to talk about a different sort of abstraction. Abstraction, the other major sort, abstraction by specification. So for this, I'm going to show a different example. But it's going to be similarly sort of austere to communicate the essentials. Okay, so we have two pieces of code where in both cases, we're doing bubble sorting to keep track of sorting some piece of information. Importantly, they're counting on ties, things that are tied still being in the same order as the original one, as they were originally. So if there are two things, there's an original order for things, and if there's two things in there that have to be sorted that are equal, they need to stay in the same order. So that code is counting on that. Okay. So we have bubble sort used in multiple places. Now, I hope your heart yearns to abstract this out for the same reason we saw, right? And for the same motivations, right? That if you go and try to change it one place, you may want to propagate changes elsewhere. Now, it's a bit more subtle here, as we'll see. So at the least, we could carve out some routine that performs this job one place, give it a face upon the world, give it a clear job in life that can be easily tested, easily debugged, easily mocked, easily built separately, easily reviewed, right? All those are good. And all of those are good. What's that? Okay. Okay. So if it's bubble sort, it's a bit of an embarrassment, as Tamer knows. It's a bit of an embarrassment because it's needlessly sacrificing performance. The same job can be accomplished much easier, much more efficiently. And once you're getting to the sort of billions of data points that I spoke about yesterday in 340, you really sacrifice huge amounts of time by doing things with a bubble sort. You're familiar with that notion, right? So maybe we say, okay, we're going to perform quicksort, and we introduce it. What's the problem? I put in place quicksort instead of bubble sort. This is one job in life, right? This is a function. Perform sorting. This job in life is very well defined. It's carved off. It's in one place. It has dignity to your code. But what's the problem with changing it to quicksort? Anyone? Yes, Colin.
Five are no longer in the same order.
Ties are no longer in the same order. Quicksort uses randomization. And ties are not guaranteed to be in the same order. And the challenge is that this change to sort, well, it has the virtue of only being needed to be done one place. That was the virtue of abstraction by parameterization. One place where we go. It breaks the uses of it here, which are counting on a property that ties, that the ordering of things of tied value is retained. So it breaks all this code. And remember, for modularity to not draw us into madness, we want to be able to carve things out in a way when we change one piece, it doesn't lead to changes that have to take place across the entire system, right? Imagine if my going offline after class to bring my computer back to my office caused all your computers to have to reboot or something. The world would be even more mad than it is. We need to have modularity and have pieces be able to use other pieces in a clear way without a change in one place having to lead to changes elsewhere across the entire system, right? Without changes having to propagate everywhere. We need modularity with some measure of independence, some measure of autonomy, right? So how to deal with this? Abstraction by parameterization is not going to cut it. We have abstraction by parameterization. We pass it different vectors here, but it doesn't deal with this issue. And it's really to deal with this challenge, to avoid modularity leading to the madness of changing one place in order to change everywhere, that we introduce abstraction by specification. Okay. Now here, you remember my notion of abstraction was hiding details, allowing reusing the same basic abstractions in many particular circumstances. You remember that? You remember that? Remember we had add vect and we could use it from, with abstraction by parameterization, we could use it from here on vec 1 and vec 2. We could use it from here on my vec 1 and my vec 2. I could use it from here on his vec 1 and his vec 2, and another place her vec 1 and her vec 2, whatever, right? We could abstract away from the particular uses, the details of those particular uses. Well, specification, abstraction by specification, we're going to be hiding details, but that details we're going to hide here, mark my words, are details of implementation. We're going to abstract interface from implementation. We're going to hide the details of what particular implementation we use, as long as we guarantee certain properties. And those properties, ladies and gentlemen, are guaranteed in a contract of sorts. So here, in abstraction by specification, I'm going to provide information about abstraction, adding two vectors or sorting an array that ensures the user of certain properties they can count on, we're calling it. We tell them what they have to provide for us to do our job, this add vectors or for sorting. That's one thing we need. Those are the preconditions, right? You give me this thing that can allow me to do my job. And then we state what the post conditions are, what properties we guarantee. If you give me what I need to do my job, I guarantee you this, right? So here, we're going to have a separation of interface from implementation. And the interface is going to specify these properties. The details being hidden here are differences between implementations. Where I have abstractions that not only allow different parameters to be passed, that's one thing, that's awesome. But more than that, they provide certain guarantees. They have certain preconditions and postconditions that allow, as long as they stay observed, we can change the implementation, as long as it adheres to those postconditions, given the precondition. Okay, so a key notion here is this interface. We're going to separate the interface, these properties we have to maintain, from the vagaries of how it's implemented. Now, it bears noting that when we specify the interface, certain basic things, like this is a function that takes a double argument and returns a double, is way underpowered. Like that does not give us firm properties we can count on. It says it needs a double to do its job, fair enough. We can't pass it a string or something, but it doesn't tell us anything about the properties of it. For example, is it returning, if I pass it a square root of, if I pass it 4.0, does it return 2.0 or could it return a pair of 2.0 and what? What else squared is 4? Minus 2.0, right? A pair. We're going to provide in the interface some way of knowing what this thing does about its behavior to avoid this risk that when we update the implementation, we accidentally break what others are counting on. This guarantee that we provide for our code, for say sorting or for adding a vector, will make certain guarantees, and those are the guarantees the users of it can count on. And those are the ones we have to maintain as the creator of the thing that sorts. We're providing a form of contract. Okay. And we're going to provide this contract through specifications. Okay. So here, recall this, right? When I substituted quicksort for bubble sort, it's true it improved the efficiency, but it broke the code that uses it, or at least some uses it. Because we didn't say what the user could count on with sort. This is wild. The user didn't know what they could count on, so they counted on ties being in the same order. They don't know what this guarantees. Because we don't know what they're counting on, we may change it in a way that's incompatible with what they're counting on. They're counting on ties being in the same order. We didn't know that when we changed this, right? So we're going to provide an interface here that indicates some sort of contract. And the key component of this interface, not the only one that's going to talk about in the class, is that it provides preconditions, the information, the guarantees I need to know about the things you pass me so I can do my job. I need to guarantee these things about that, the preconditions, including the values being passed in. And post conditions that I guarantee if you meet those preconditions, if you've passed me values that are not null, I will guarantee these post conditions. and here I'm looking at sort indices, the index in which that element originated. Yeah. Which is a slightly different thing, but it's very closely related to this issue. So here I pass in values and I provide these guarantees as long as you observe the preconditions. And here we might use a bubble sort for this, or we might use a merge sort, and those guarantees are maintained. Why do I say those guarantees are maintained with a merge sort if we go from a bubble sort to a merge sort? Colin may know. Merge sort, what does it guarantee about ties? They are indeed in the same order, it turns out. The ordering is maintained. Quicksort, by contrast, would not be allowed. Do you understand this? That would be an illegal, that would be contrary to the guarantees, to the properties that I'm guaranteeing, that values that are equal retain their original order. That would be contrary to what the promises, the properties that I'm supposed to guarantee. So this will be ruled out as an implementation. Merge sort will be allowed as an implementation. Radix sort would probably be allowed as an implementation. I'd have to think about it, but I think that's true. And there's other types of sorts. Okay, so do you understand this notion of abstraction by specification? This allows many uses of the same abstraction. And it hides the implementation. It allows any implementation that meets these criteria, these properties that are guaranteed. As long as it abides by the same post conditions, given the preconditions, I can modify this. That's something more than what we had before, where we had parameterization, abstraction by parameterization. We could pass it different things, but we couldn't prevent it. And there was no way of encoding what's a safe change here. We didn't have a way of abstracting over this implementation. If we change the implementation, it could break everything. Now we have that guarantee. We can know what changes here are legitimate and what changes are ruled out. We know what properties others could be counting on out there when they're using ours, because we're saying these are the properties you can count on. And that gives them the ability to count on them without worrying about how this code will evolve. And it gives us the ability to evolve this code in certain ways without worrying it will break things. And it prevents the folks who are using this code forever to look at the details. Right? Are you comfortable with that notion? Right? It's kind of like if I'm using FedEx to ship a packet. I don't have to, and I don't want to know all the details of the local Saskatoon FedEx. I don't need to know the details of when their planes run, or where exactly they're shipping the packages, or when the trucks go to the airport, or what's going to be delivered by vehicle, land vehicle versus air. I don't want to have to know that. All I want to know is the guarantees, right? If I get it to them by 2 p.m., it'll be delivered to Toronto by the next day by noon or whatever. I don't want to know the detail. I don't care if they have a hot rod that shoots across the country, or they send it via train, or a really wicked fast horse and buggy. As long as it gets there, I need to know those guarantees, and that insulates me from needing to worry about the implementation. Right? Because time is limited. In order to write A over here that uses B, C, and D, I shouldn't have to know all the implementations of B, C, and D. And I shouldn't have to know when they change for me to change my code, and them changing B, C, or D shouldn't break my code. Basic matter of sanity. We need modularity without it meaning madness through propagating changes, or changing one thing breaks everything else. Are you okay with this idea? hiding implementations by providing specifications that provide certain guarantees. What you need to provide for it to do its job, and given that, what properties are guaranteed as a result. Are we comfortable with this? I think you should have seen this before as well in 270 or 370. Sorta? Kinda? Okay, well, I'm glad I covered it. Okay. So there are lots of wonderful benefits. I mean, like chocolatey goodness. I mean, it's really, it has diverse benefits, right? You have locality. You know, if I go and I change the implementation to my sort routine, I don't have to worry about having to go change across the entire code, right? I can work on A without having to know all the details about B, C, and D. All the details of their implementation. Allows me to focus on my job, talk about separation of concerns, allow me to focus on my concerns without getting all mucked up with your concern, with your details. It allows me to build A without knowing B, C, and D are built yet, or without them being built. Why does that allow? Why does having this interface that provides certain guarantees about, say, what B does, what C does, and what D does? Why does that allow me to work on A, even if they're not yet built? Yeah, speak on, Connor, with an E.
Because then like the person writing the code knows what to send in, the person using the code knows what they'll give back.
Yeah.
So each side kind of knows what needs to, like the contract that you're saying.
Yeah, they know what each of them needs to know to do their job, right? And they can create that code accordingly. Modifiability. They can modify their code without breaking code all across the system, without having to alert people all across the system. I've changed the sort. Prepare, watch your code crumble, right? No. And there's ability to reuse, right? You can have shared code that actually calls off to many different things over time because they all adhere to the same interface. And it's just written against the interface. And you can pass it in anything that meets that interface, and it will call through that interface with that same contract. So when change occurs, we have to only modify the abstractions, not the code that uses them. Now, to do this well requires some notion of software contracts. Contracts define this agreement between the implementation and between what we're providing and the usage. And they're described by specification. And there's many types of these sort of contracts. From the very basics of pre and post conditions and invariants and history properties, something we'll be talking about later, all the way down to things like quality of service contracts, where you guarantee certain timing or certain, uptime or what have you for sites, for services. Okay, but what I'm going to need in this class, what I'm going to look for, what I exhort you to provide, what I'm going to require you to provide are these sort of specifications. Okay. And this is going to be true at the level of functions, but it's also going to be true at the level of classes. And classes are going to have some additional mechanisms. They're going to have history, properties, and invariants associated with them. But we're going to see that often with APIs, we declare an interface for a bunch of functions at once. Mm-hmm. So we say this layer, the system, the repository layer implements these methods or these functions. And they have these preconditions to call them. And they achieve this as sort of a post condition. Okay. So within object-oriented languages, we declare interfaces, and this says basically what services are provided by something, right? So if we have a class, it can implement one or more interfaces, and the interfaces indicate what functionality has to be provided, right? Are you familiar with this notion generally in object-oriented programming? An interface will be a sort of contract. It will say, okay, I support drawing, I support disappearing, and there's a separate interface that says I support serial numbering by giving an ID. And then I might have a class that implements presentable, and that means it has to provide a draw and a disappear. And it also implements serial number and has to provide an ID. Is this familiar with you? This too is a separation of interface from implementation. Often there may be another class Y that also implements presentable. And if there's some code that can deal with any presentable, I could pass it an instance of class X, because that's a presentable. Or I could pass it an instance of class Y, because that's a presentable. And it could do its job. That separates interface from implementation. Whether class X or class Y, all I need to know is that they're implementing presentable. Is this notion familiar? Kind of, yeah, okay. Right, so the set interface can be implemented by many particular sets, right? Abstract set, copy on write set, enum set, hash set, all these different implementations of sets may be optimized for really large sets or small sets or in-memory sets or what have you. Okay, now when you design these specifications, there's a need to balance how much information you provide. So tell me, what's the downside of providing too much information? Or too many guarantees, too many properties that are guaranteed? What's the downside to the creator of that abstraction? What is it like? Why could that be a pain for them? Yes. Oh no. Okay. Hold on. Oh, Jason. Yeah. Okay. I for some reason Simon was. I think it was because it had the same string length. And it ended with the same two letters. Anyway, yeah, the one part. Okay, speak on Jason.
Yeah, I would say one of the issues of it having, I guess, too large an implementation is just almost like it's difficult to make this like out of scope. And also if you need a specific use case you want to extend it, like maybe there's something that only wants to extend parts of the functionality, but not the entire thing.
Okay. Okay, so yeah, I think you're dealing with one part of it. I was seeking to focus on providing too many properties, too many guarantees, but I think what you're saying is providing too much functionality as part of that. May mean that it's overextended, right? It's not divided up into natural chunks of work. It's trying to be the kitchen. It's trying to be the jack of all trades, whereas really there's a set of sort of naturally carved out functionality to be better split up and allow implementations to evolve separately, for example, for it. But I'm thinking particularly about promises, like we saw sorting before. What's the matter of what's the problem with providing too many guarantees, like saying, I perform this with a sort that is rated sort, or I guarantee that this is performed with quick sort. What's the matter? That's a very strong guarantee. It's a very strong property to count on. What's the matter with that? Yes, Tanner.
I can't ever change it.
Yeah. It limits your ability to evolve it. Sometimes you really do want to evolve it in ways that give you performance advantages, or lets you have lower memory consumption, or faster code, or maybe make it more transparent. And if you're providing too many promises, it really limits your options for how you can evolve it, right? How if you don't provide enough guarantees? What's the problem there? How if you don't say whether or not it preserves in order, does it preserve the ordering of things that sort to the same value? Yes, Connor with an E.
Then somebody might use it wrong. Somebody might use it as if it's a bubble source, but then if you intended it for a quick sort, but then you actually had it as a bubble source, they are using it that way, so it works that way.
Right. So if we provided minimal, like no guarantees here for what this does, people may jump to assumptions about it. They may tacitly assume, well, it doesn't tell me what it does. I'm going to guess what it does. Maybe they call it. Like, what would be the matter of calling raw and say, oh, that's what it does? Or, passing it an argument and seeing, oh, it allows nulls. I guess I can pass it nulls. What's the matter with that? Like, what's the matter with just testing it and see what it accepts and just using that? Yes, Connor.
Then you can't change it.
Then the implementer of it can't change it because people may be counting on this weird aspect of behavior. So providing guarantees actually gives freedom to the creator of the sort routine or the add vector routine. It tells them what things they can't change, but by extension, if they haven't promised it among the properties, they can change it. They can evolve it. It gives them the flexibility to change a lot of inessential things, or a lot of things that they want to provide strategic flexibility to change because they want to optimize it, or they want to make it parallel, or they want to have it be low use of memory. Okay. So you want to balance how much information you provide, not too much, not too little, in sort of a Goldilocks type of way. And you also want to be careful that you don't make it so complex how you specify its rules that people aren't going to want to use it, or they won't even pay attention to what those properties are, right? So specifications specify guarantees in which the users get the abstraction can count. And it reduces this guesswork and the need for them to look at your code to see, oh, that's what it does. Now I know how to use it. Look, time is limited. Working on complex software is hard enough. We shouldn't have to go look at someone's code to know how to use it. All right. All right. All right. Live up to that exhortation. Because not all code I saw could be understood without reading it. Not all code I saw had nice descriptions of what it did without guaranteeing exactly how it did it. I should be able to know what it does without getting all involved in the exact gory details, the brutal details, the extraneous details of exactly how it does it. And it's dangerous because if you count on exactly how it does it, it can't evolve, right? And now we've coupled the details, the gory details about B, C, and D do things. And that way, as Shakespeare said in King Lear, lies madness. Although, to his credit, King Lear probably wasn't talking about software engineering. It's the primary focus. Okay, so I think you get the basic ideas here. I'm going to be giving you in a maybe I'll say one more thing here, and then I'll say where we're going with this. This is actually from a diagram. I don't know, Colin will remember this, but I think Connor was here as well. But where we have a piece of code, and the idea is that we have an interface, call it I, that promises certain functionality, like it knows It promises, it can initialize things with certain arguments being passed that have to meet some properties, and it can send messages if you pass it certain things. And I can pass into foo a particular instance of that interface, something that implements that interface. It could be in a class, an instance of class, an object of class B or B prime or B double prime or B triple prime. Doesn't matter, as long as they implement the interface, I can pass them into this code, and this code will still work, right? This code will still run. This is called a dependency injection type of setup, where I pass in an instance of something meeting this interface, and then I can use that through the interface without coupling it to whether it's a B or a B prime or B double prime or B triple prime secretly behind the scenes. I don't have to worry about that. This same code will run. But in order to do that in a sane way, we have to know what properties are guaranteed. What does initialize need to do its job as its precondition or its send message, okay? And there's many benefits, and I'll post these slides. Easier integration, easier understanding of code, conceptual clarity, easier testability, easier debuggability, easier mocking, and all these sort of good things that can occur. And it can help us run things faster. So, these interfaces appear in many places, including layers of systems, and I've talked about this before, but a data access layer. And Alex, RTA, provided a nice post on repository pattern that illustrates this, and she also, per request, provided links to 3-tier applications that illustrate this separation. We have a service layer, business logic that's behind an interface, so we can evolve its implementation, and a router behind some interface, so we can evolve its implementation. And the service layer can call down to the data access layer. The router layer can call the service layer, and in all cases, they're calling through an interface so that we can evolve what particular implementation we have. We could mock out the database so it just writes to a file, or at other times have it go to a real database for production or for testing. Okay. So those are all the comments I have on this particular set of ideas. I hope that would be clear, the motivations for abstractions, and abstraction by specification, as well as abstraction by parameterization. What's expected of you? Well, I'd like you this very afternoon, for the tutorial to think about where do interfaces fit into your system. Are there natural layers to your system? How soon could you start defining them? I made the argument over here that by defining interfaces for B, C, and D, we can actually start on A sooner, because we know what it can count on here, what to call. I want you to think about this, and I want you to come up to me on Thursday, be able to say something about where interfaces lie in your system. And then on Thursday, we're going to go through another exercise as well. We're going to talk about this. I want you to think about it in the tutorial time and between now and Thursday. And then we're also going to talk about testability, okay? For some in-class exercises. That's all for today. Thank you, everyone. And I'll post these slides.